In this shorter video, we remind you of what it is to have a varying force of interest and compute one example. So I'll step off, please pause, copy the notes down in your notebook, and then press play and listen to the explanation. So in chapter 4, we talked about force of interest, and this was when you took a compound interest rate and started compounding it more and more and more times every year. So letting your M, number of compounding periods, go off to infinity. And what happened is we called that continuously compounding, and the interest rate involved was called a force of interest. And we had an accumulated value formula for it. It was a bit more complicated than some of the other ones have been. So the accumulated value at time 2 was equal to the accumulated value at time 1 times e raised to this integral power. And it's the integral of the force of interest. It's the definite integral of the force of interest evaluated from time t1 to time t2, where t1 is the earlier time from t2. Now, when our force of interest was not varying, when it was a constant, like 0.03, 3%, this formula is simplified because the definite integral of a constant is simply the constant times t2 minus t1, right? And you can try that with e to the integral from like 1 to 8 of 0.03. You'll see it's 0.03 times 8 minus 1, all right? So when the force of interest was a constant, we normally wrote delta t as just a delta, and we had a slightly simpler formula, all right? The book also uses r sub t, or r, for the force of interest and constant force of interest. All right, well, here's an example with a varying force of interest. So we begin with a force of interest given by delta t equals 0.1 minus 0.02 times t. And this force of interest is at work from time 0 years to time 4 years, all right? So we'd like to determine the accumulated value after 3 years of $1,000 deposited at the end of the first year, all right? And that wording might not be as clear as we might wish, but that's just the way the textbook and exam FM sometimes are or is. So here's our situation. From time 0 to time 4, we know the force of interest that's in play. At time 1, we know $1,000 is received. And we'd like to know the accumulated value after 3 years. Okay, so starting at time 1 after 3 years takes us to time 4. All right, so we're going to take $1,000 and try and push it forward 3 years using the force of interest. Okay, so I know AV1, I know delta t, and I'd like to know AV4. So applying the formula, the accumulated value at time 4 is the accumulated value at time 1 times e raised to the definite integral of delta t evaluated from 1 to 4. All right. Delta t is 0.1 minus 0.02 t. And now off to the side here, I'm just going to crank out that Calc 1 definite integral. So the definite integral 0.1 minus 0.02 t, well, first off, an antiderivative is 0.1 t minus 0.02 t squared over 2, evaluated from 1 to 4. So I plugged in 4 minus, plugged in 1, make sure that subtraction sign acts upon the entirety of plugging 1 in, so parentheses are helpful. And that cranked out to be 0.15. So I can replace this definite integral in the exponent with the number 0.15, right? So the accumulated value of time 4 is 1,000 times e to the 0.15, which cranks out to be $1,161.83, right? Now, when you have a varying force of interest, you have to respect the clock that's ticking, all right? So you cannot simply reset the time to be time 0 at the time of $1,000 deposit. Because yeah, I mean, I agree with you. It's much nicer to have one of the bounds be a 0. But we're not allowed to do that because this force of interest is a function of time. If you're going to change how the clock is acting on the bounds, you have to adjust the force of interest as well. And that's simply going to be more work than it's worth. So I'm simply going to use the time values they provided in the problem because the force of interest is linked to those particular time values. The force of interest at time 0 is very different than the force of interest at time 1. So of course the money will grow differently during these time spans as well, right? So if you would have hoped to have done the integral from 0 to 3 of that force of interest, you will get the wrong answer. So you have to follow the timestamps provided in the problem when you have a varying force of interest. In everything else that we've done, constant force of interest, compound interest, compound discount, all you needed to know was how long that interest rate was working on the money, not from what year to what year. It didn't matter if it was from year 1 to year 4 or year 0 to year 3. Money that at the beginning of the period could be pushed to the end of the period with 3 years worth of that behavior. With the varying force of interest, we have to know which 3 years we are moving through because our varying force of interest differs over each of those years. It's varying. Okay.